Okay, so let's look at an example of how to find a matrix representation. This comes once again directly out of the Mike and Ike textbook. This is exercise 2.2. And one thing to note, so in quantum computing, quantum information, we denote this special vector that we label with a 0 in the middle as the vector 1, 0, and this vector that we call 1 as 0, 1. You can think of this in some sense as being kind of like, X and Y, right? So if I have some grid, right, in some ways, I can think of this as being my my 0 vector, and in some ways, I can think of this as being my 1 vector. Now this gets a little more complicated because in general, we're going to deal in complex spaces, so it kind of muddies this picture a little bit. But for the time being, 0 and 1 are a basis set, right? They are basis vectors for this two-dimensional space here. And they just happen to label this as 0 and label this as 1. 1, 0 and 0, 1 in that fashion. And that's because, computer science for a long time has used the idea of binary information. So computers deal in zeros and ones. So that's really where the labeling comes from. And it's unfortunate, but just try not to be confused by that. So with that preface, so let's imagine that V is a vector space with basis vectors 0 and 1. It's some linear operator A, which works in the following way. A takes the vector 0 and turns it into the vector 1, and A takes the vector 1 and turns it into the vector 0, right? So where we would start with this, or where I started with this, I should say, is, let's take A0 equals 1. And since we're in 2 dimensions, we know that A is going to be a 2 by 2 operator. So let's rewrite this as, I'll give these letters A, B, C, D. So these are the 4 entries of my matrix, acting on the 0 vector. And that is going to equal the 1 vector. Right? So all I did was, I'm just saying, hey, my A operator is going to have a matrix representation. It looks something like this. It's a 2 by 2 matrix. My 0 operator, my 0 vector is 1, 0. And my 1 vector is 0, 1. And so using the rules of matrix multiplication, I could say that, well, let me multiply these together. So what I'm going to do, I'm going to take this top row and multiply it by this column. And so that's going to give me, let's see, A times 1 plus B times 0. Okay. That's my top entry. And then I'm going to do the same thing for this second row here, right? So I'm going to take this, turn it sideways, and multiply the various terms. I'm going to get C times 1 plus D times 0. And so that equals AC. Now AC equals 0, 1, right? Because that's what we said right here. And so what I then find is that, the letter A, so this entry right here, A, must be 0. So I'll put this over here. I'll put it in red. A equals 0 and C equals 1. Okay, so we have the first 2 parts of our matrix A. So let's do this again. Let's do it one more time, and let's do it now for the case not where A0 equals 1, but the second case, A1 equals 0. So A1 equals 0, right? And again, A, B, C, D. But really, I can make a substitution here. I know that A equals 0, so I'm just going to put 0 right there. And I know that C equals 1. So I'm just going to put a 1 right there. Now, when I multiply by the 1 vector, which looks like this, I'm going to get the 0 vector, which looks like that. Okay, so let's do it all again. Let's take this first row, flip it sideways, and multiply it by this column. And we're going to get 0 times 0 plus b times 1. And then down here, we're going to get 1 times 0 plus d times 1. And simplifying, that's 0. So we get b d, this vector bd equals 1, 0. Well, hey, that's great. As that tells me that vector b equals 1 and vector d, or component d, letter d, equals 0. Okay, great. So I can write my matrix A. I can write my matrix A as a 2 by 2 grid. So A equals A, little a is 0, B is 1, C is 1, and D is 0. Fun fact, we also call this a NOT gate. Meaning, if you give me a 0, then I want not 0. If you give me a 1, then I want not 1. And 0 is not 1, 1 is not 0. So we have created the NOT gate.